Okay, so the next problem in the lead code we are solving is flattened binary tree to the linked list. Okay, here we have given the binary tree. We need to convert it to a linked list. Okay, so the condition is it should be in a pre-order traversal. As we know, like I mean, we can represent the tree in array, right? Array format, and we can mainly represent like I mean, we have a three modes of it, right? Like I mean, pre-order, post-order, in-order, correct? So what they are asking is we need to represent this in a pre-order mode. Okay, let's forget about linked list. So if we are aware of how we can convert this to the pre-order, right, then we have some basic clear. So once we got so I mean once we got that array, right, we could have simply converted to the linked list, correct? That is also like I mean this is the problem. Okay, but now the problem here is I mean the condition restriction here is we are not supposed to create a like I mean build a list of pre-order cell and then convert it to a linked list. Okay, that's not meant to be done here. Here instead what we need to do here is we need to do it in place, meaning whatever the route they gave us, we'll have to update it such a way that we result into this condition. Okay, so ultimately this should be in a pre-order traversal manner. That is a condition and we should be doing it in place. Okay, let's see how we are going to do it. So when it comes to pre-order, it means that this is the order, right? Like I mean we should traverse from root first and then left and then right. So if you are even though if you are going to build a list, right, let's say that if you are going to build a list, it should be like this. Okay, root should be here and all the left tree elements will come here and all the right tree elements will come here, right? So even though if you see it here, we know that 2 3 4 are coming from the left tree, correct? And whatever the left here is, that is from the right tree, and this is the root node, correct? So now what just happened here is we have the root in place. Okay, and 5 6 also, let's say that let's not consider, it's already flattened. Okay, let's say that let's say that for now. Okay, 1 is there and 5 6 is all there, but left tree is missing here, correct? Left tree elements are missing. Like I mean in the result, if you check this path, right, we are doing it in place replace. Right is there, root is there, but left is missing. So what we are going to do is we are going to flatten this also, solve this and push it inside here. Okay, like I mean we'll see like how we are going to push it in the code. So basically what we are going to do is like I mean once we have this tree node, right, so what we can simply do is um now what we can simply do is we can detach this node, whatever that is node, right, we can point it to the, like after we flatten it should be looking like this, something like this one, correct? It will be looking like this. What we can do is the 5, whatever the node 5, we will attach to this one. Okay, 5 will come here and 6 will come here. So we, once the left tree is sorted, we can just update our right pointer, like I mean node dot right is equal to node dot left. So everything will be copied from the left to right. So this is how we are going to copy. But what is the one takeaway that we need to take here is, so here it has been asked that asked to build a traversal like in the pre-order list. Okay, and we have a root here and we have already a right node, we don't have a left node. So we are going to flatten the left tree and we'll insert it. Okay, now first understand how we are we going to flatten this at first place, correct? So let me clear this out. Okay, to solve this, right, let's break down the problem. Okay, like as whenever it comes to the tree, we are going to solve this via recursion, correct? And also like I mean let's not go straight away to this. Let's say first what we'll do is we'll solve this portion. Like ultimately will be we need to flatten this tree, right? We'll need to flatten the left tree and we need to insert it. So how are we going to flatten this? How does it even look like, I mean after flatten? Like I mean we know that as it's a pre-order, right? So the first thing will be 2 and then next thing will be 3, correct? 2 left 3, sorry, this is not there, and 4, right? The like I mean after traversal it should be 2 3 4. So ultimately how it should it look is 2, I mean we need to build a list, right? We need to, after flatten, we should be doing this one. Okay, and like I mean we can apply this same logic to the top level. For now let's assume whatever that is given in the red, right, this is the given problem. Okay, so after flattening this is the answer for us, correct? So now what we have done here is um we need to get a tiles basically. Like I mean whenever we solve, right, we need to insert we need to perform an insertion option operation here. We need to know what is the tile node. Like I mean let's say that in this case this is the tile node for us, correct? So if we know this one, right, this is the tile node, we can just say dot right is equal to 5. So the fifth node dot right is equal to fifth node. If I just do this, it will be pointing to this will be easy for us, right? Like I mean we can just insert operation here. 4 is pointed to this, so we are seeing this link here. And finally what we can do is this is the parent node, right? Top node. I can say that one let's one point to this node. Okay, so ultimately how it looks like, this will be the list. So this is how the insertion operation is working. So like, I mean, basically what I'm trying to convey is we need to make sure that whatever we flatten it, right, once we flatten, we need to be keeping the track of the tile nodes. If we get to know the tile nodes, it will be easy for insertion. Okay, now let me clear this first. Okay, now let's understand how we are going to even swap, right? We got to know that we need a tile node. Okay, so obviously, like in this condition, so this will be the tile node, right? This will be the left tile and this will be the right tile. Okay, so now let's say that we got to know that this is the left tile and right tile. How are we going to solve this? So we need to flatten this, right? So what is the thing that we'll first do is we'll make sure that whatever that is 2 is pointing to the, basically ultimately what we are going to do is 2, 3 and 4, correct? While we are doing this, we should not be losing the reference, right? So what we'll do is we'll first move this node to the here. Okay, so whatever that is 2 is pointing, it can be something like 5 is 5 might also be here. Okay, it is already flattened one, you need to think it like that. Okay, so basically, so 2, 3 and some list is here, so I don't want to lose any reference. So what I will do is whatever that is pointing to here, right, like, I mean, I will move it to the left tile first. So how it should look like is 3, so 2 is here, and 4 will be still here. Actually, we are not deleting or anything, so 4 and 5 will also be here. So left one, right, left one will be 3. Okay, 3, it is left is pointing to none already, right one will point to this one. Okay, so it will be looking like this at this moment. So we need to, so we are trying to insert the left tile in between the root and the right one. Okay, so it is currently pointing to this. So once we are done with this, what we can do is we can update left dot right is equal to left dot I mean root dot right is equal to root dot left. Okay, so what does it mean? So we'll simply moving this pointer, whatever the pointer here, right, will be pointing to this one. So it should look like this now. So 2, let me, yes, so it should look like this now. Like, I mean, both the left pointer and right pointer will be pointing to this one. Okay, so at least you can see that we were able to serialize, flatten this old tree, right? 2, 3, 4. We were able to flatten it like this, 2, 3, 4. So only thing that is now left is we'll have to shift whatever that is in the left, right. Like right pointer is already pointing to this. We'll just have to make this as a none. So ultimately, it will look like this one. Whatever we discussed so far is this will look like this one. Okay, so yeah, we were able to flatten the left tree. Similarly, like if it be taken in a big picture, right, so let's say that after solving this, how the tree will look like is, okay, so this is how it will look, right? Like after flattening it, we flatten this one. Now it is looking like this one. So now again, what we'll have to do is, like we'll have to. This is the big tree. This is the main tree, and this is the left tree, and this is the right tree. Correct. Now we should be knowing what is the tile node here. Okay, this is the tile node for us, and this is the right tree. So we are going to apply the same thing here. I'm not going to rewrite it, but ultimately it will look like this. Okay, 4 will be initially will be pointing to this one, 4, 5, 6, and right pointer will be pointing to this one, and then we'll finally cancel it out. So it should look like 1, 2, 3, 4, 5, 6. This is how it will be looking at. Okay, now quickly check the code how it looks. Okay, now we can do it. So yeah, like, I mean, we are going to solve it via recursion, obviously. So flatten, and we are going to get a root here. So first most foremost thing is, if there is no root, we'll be returning none. Okay, and then next thing is we'll doing the left side calculation and also the right side calculation. Okay, and finally, let's say that if there is something in the left, we need to insert it to the right side. Correct, this is that logic. Okay, if there is something in the left, so we'll be pointing the left tile to the right side, we discussed, right? Left tile, whatever that is the left tile, right, will be pointing to the right side of the root node. Okay, that is there. So yeah, left tile dot right is equal to, we pointed it out, and then finally we'll point the right pointer to the left node, and we'll be initializing it. So this is just a code for insertion. Okay, and now what we'll have to do is ultimately we need to get the tile again. Correct. So we did some calculation here. Okay, 2, 3, 4, but we need a tile node always, as we said. Correct. So for that, what we'll have to do is we'll always have to return the right tile node. Okay, let's say that if there is no right tile node, we'll have to return a left tile. So what does it mean is, let's say that 2, if it was only 2, 3, okay, 2, 3, 4 was not there. Okay, 4 was not there, so there is no right tile. Correct. So in that case, 3 will itself will act as a next possible tile node. Correct. If 4 is not there, 3 will act, so it means we'll have to return a left node. Even if the left tile is also not there, 3 is also not there, the next possibility is 2, so we'll have to return it. So that will be the condition ideally for the leaf nodes. Okay, like a left tile will be also be empty, right tile will also be empty, so we'll have to return the leaf node in that case. Okay, so yeah, that is it actually, the problem. if you just analyze it, right, like, I mean, it will be more clear actually once we write the code and analyze it. Okay, so this is it. Thanks. Yeah.